Hello students and welcome to a very powerful test for series. It's called the ratio test. Now the ratio test is ideal and it will be the perfect tool to think about it whenever you see in your series that you have n factorial or you have a number to the power of n. So you have a number and then to the power of a variable. That's a good place to think of the ratio test. And the ratio test can be used in a very simple, elegant way. You need to find two important things. First of all, in the denominator down here, you write an as it is in the question. In the top, you need to write the same thing, but you replace every n with n plus 1. So replace n with n plus 1. So whenever you see n, take it off and write n plus 1. Usually I prefer to write it between brackets just to make sure that I keep track of my changes. Now, you will get a limit of two things. You will use maybe L'Hopital to solve it, and then you will get an answer. Now, the answer could be many of the answers. Maybe the answer will be less than 1. Of course, it's positive because I put absolute value. So here I can do the alternating, I can do the positive without any problems. Now, if L is less than 1, the series converges. You just have to stop and say the series is convergent using the ratio test with L less than 1. Now, if you get L is greater than 1, including infinity, because infinity is greater than 1, then you have to stop and you will say your series diverges. Now, the worst case scenario is when L is exactly 1, and in that case, the test is inconclusive. We don't know if it's converges or divergence using this test. So what shall we do? Let me just write it in green here. Use another test. It might be another test will give you the correct answer, but this test, it doesn't work for you if L is equal to 1. So while this test is really powerful, easy to use, sometimes we get into the trap that the test is inconclusive. And with the practice, you will know whenever you see the series, you will know which test to use. Let me go ahead and show you a simple one here. Look at this series. Once I see a factorial, the first thing came to my mind is the ratio test. Remember, we said the ratio test is ideal for these things. Okay, so we have just to find the limit. So let me go ahead and find the limit. So I need to find L. What is L? Is limit as n goes to infinity, an plus 1 over an equal limit. Now, before I find the limit, let me just, this one is an alternating series, because if you take the n over the minus 1 and over the 3, it's clear and alternating, and the absolute value will give me the positive part. Now, as we said, down here we have to write an as it is. So I will write negative 1 to the n, 3 to the n over 2n plus 1 factorial. Now in the top you have to write the same thing, but replace every n with n plus 1. So n plus 1, 3n plus 1. Here we have 2, I replace only n by n plus 1, and then there is a plus 1 before. That's exactly. So imagine you take this off and you write n plus 1. That's what you get. Now, before we do anything, do you remember if we have stack out of 4? So we have numerator of the numerator, denominator of the numerator, numerator of the denominator, denominator of the denominator. We have a stack of 4. The first one will be with the fourth one, 2 will be with 3. So we take the first one with the last one. Now the first one is this one, negative 1 to the n plus 1, 3 to the n plus 1. And then we have this one. If we just take the 2, it will be 2n plus 3 factorial. The one in the white will be 2n plus 1 factorial, negative 1 to the n, 3 to the n. That's how we do it. We take the second with the third, we put them down, the first and the fourth, and we put them up. Usually I prefer you write the same quantity over each other, because now the cancellation, that's what will work. So the cancellation is going to work here, and if we start cancelling, that's what we will get in this example. So the next one is that what we need to do now, if you look at the minus 1 to the n, minus 1 to the n, and 3 to the n plus 1 and 3n, there is a clear cancellation, very clear cancellation. The cancellation is we take the 3 to the n and the 3 to the n, negative 1 to the n, negative 1 to the n. Let me just go ahead and write what we will get. Is that, I think that's what we will get here, is 3 in the top. Oh, there's also a minus 1, so it's going to be a minus 3 in the top. Nothing will survive from the bottom. Now, this one, I will use the factorial reduction formula. Let me now just remind you of the factorial reduction formula. I will write it down here, and then I will just take it away. 2n plus 3 factorial. You remember we said we can expand it a little bit, meaning you can write it as 2n plus 3, and then you can take something less, so it's plus 2, and then you can take as much as you want, and then you stop with the factorial. Now what I want to do, I want to cancel this one, so I will need to write it down here. So 2n plus 1 factorial. Remember, we can take the factorial, subtract 1, and we can stop whenever we want. If you don't remember, go back to section 11.1. We did that there, very much clear. And that's all what we need to do. We keep the one in the white as it is. And the one in orange here, it will be 2n plus 3, 2n plus 2, and then something that get cancelled. Remember, the goal is to cancel something. And now I can't cancel it. Now, absolute value with the negative sign, this would be cancelled. So I don't need even to write the absolute value. I'll just take the limit n goes to infinity of having 3. I don't need the absolute value, it's already there. Actually, 3 is in orange here. 2n plus 3, 2n plus 2. And finally, the final answer is 3 over infinity, which is simply 0. Now remember, 0 is less than 1. So what does the ratio test will tell us in this example here? The ratio test will tell us that the series, so I will write hence the series is convergent because it's less than 1, and you have to write the test. So it's convergent by the ratio test with L less than equal to 0, less than 1. You need to write this statement here, all of it. all of this statement, you have to write it down. It's very, very important you write it down, this statement. Okay. So just keep it in mind. You have to write the reason and how you find the limit. Okay, I think that's straightforward. Let's do another one, which is this one. Now this one, as I said, we have a number to a variable, number to a variable. So it's the ratio test could be a perfect trial here. Let us do it. Solution. We need to find L. What is L? Is the limit n goes to infinity of an, and in the top I will put an plus 1. Next. In the bottom is easy. I can put something very, very simple on the bottom. No worries. It is 10n over n plus 1 for 2n plus 1. Now the one in the top is 10n plus 1. So instead of n, I just need to replace every n I see with n plus 1. Remember, I put it in a bracket so I don't mess up with another number, especially if it's not clear. Here you have 2. It was 2 times n. Now it become n plus 1 plus 1. So that's exactly what we have here. Now again we have a stack of 4. 1, 2, 3, 4. Okay. So we just need to do what is necessary for it. Of course, now I don't need the absolute value because everything is positive, so I'll just remove it. I have 10, n plus 1. I have n plus 2. I have 4. If I distribute the 2, it will be 2n plus 3. And then the one in the white will be 10n, n plus 1, for 2n plus 1. And now this is very easy cancellation. 10n, 10n. 4n plus 1 with 4n plus 3. So I will cancel the 2n, 2n, and then have 3 and 1. So it will be just simply as this one here. N plus 1. And then down here I have n plus 2. And 4 power 2. Now I think this is a very easy, very simple use L'Hopital rule. The answer will be 1 over 16, which is of course less than 1. Now if it's less than 1, what we will do? We will simply go back and write hence the series converges using the ratio test with limit equal 1 over 16 less than 1. You have to write this one as it is. It's very important you write your reasoning as required. Okay, now we finished from the second question in the ratio test. Let us do some more questions, I think. It would be nice to do more. Oh, we do this one. Oh, that's a nice one. And then we will do this one here and this one. So we have 3 more questions. I will do them in the next video here. Thank you.